John Leazer serves as the Director of the Sustainable Technology Division for US EPA, and that's in Cincinnati, Ohio, actually. In his current role, Dr. Leazer oversees and develops the division's research portfolio, consisting of such research areas as green chemistry, nanotechnology, green infrastructure, life cycle assessment, supply chain design, and sustainability metrics design. Prior to joining EPA, he worked as a process chemist for Merck, where he is credited for being one of the company's pioneers in green chemistry. And just a little blurb about what he does over there. I'll let him obviously amplify on that. It says EPA scientists are charged with solving real-world problems related to human health and the environment. Additionally, they are also challenged with solving these problems in a manner consistent with the principles of sustainability. Green chemistry addresses the fundamentals of most of the work done within EPA's chemistry research programs. Green chemistry, first conceived within EPA, has taken a prominent position within EPA and the entire chemical research community. Advances in green chemistry have reached new levels in the scientific community and society, thereby resulting in unprecedented innovations in chemistry, materials, economics, pollution prevention, and human health. EPA researchers have taken a leadership role in development of numerous systems that have fundamentally changed chemical research, excuse me, as well as business practices in many sectors, such as waste remediation and water decontamination.
All right. Lynn, I want to thank you for the very kind introduction. And Clinton, I certainly appreciate everything you've done thus far. I'm always appreciative for the opportunity to talk to people about some of the green chemistry work that's currently underway within the laboratories of the United States EPA. Start by saying that green chemistry embodies all of the principles associated with sustainability. You know, sustainability is based on a very simple principle, and that principle is that everything that we need for our survival and well-being depends either directly or indirectly on our natural environment. Now, sustainability creates and maintains the conditions under which humans and nature can exist in a productive harmony that allows for the fulfillment of the social, economic, and other requirements of past and future generations. Now, sustainability has emerged as a result of significant concerns about the unintended social, environmental, and economic consequences of population growth, economic growth, and consumption of our natural resources. In the early years, EPA acted primarily as the nation's environmental watchdog, striving to ensure that industries met legal requirements to control pollution. Now, in subsequent years, EPA began to develop theory, tools, and practices that enabled it to move from controlling pollution to preventing pollution. So today, EPA aims to make sustainability the next level of environmental protection by drawing on advances in science and technology to protect human health and the environment and promoting innovative green business practices. And again, I'd like to reiterate that point, that green chemistry falls under this umbrella of sustainability. So what is green chemistry? Green chemistry has oftentimes been described within the context of new technologies. But green chemistry is not necessarily beholden to ionic liquids, to microwave technology, to supercritical fluids, to biotransformations, or to any other new technology. Green chemistry is outside the techniques used, but rather resides within the intent and the result of the technical application. Now, many people, and I'm sure including some of you on the call, may view green chemistry as just something that good development or good process chemists do. But while enabling greener syntheses, good development chemistry is not necessarily the same as green chemistry. So a robust and efficient, cost-effective chemical synthesis is likely to be accepted as good development chemistry or good process chemistry. However, that same process, when examined more rigorously with the principles of green chemistry in mind, typically brings to light some potential improvements relative to environmental performance. So processes may evolve and become greener relative to earlier iterations, but only an ideal process itself embodies green chemistry. So green chemistry is more than simply good development or good process chemistry. Green chemistry is the highest efficiency potential that exists for each chemical process, serving as both an inspiration for and the measure of the best development chemistry. So green chemistry is essentially chemistry for the environment. In many ways, green chemistry is a philosophy or a way of thinking. It's not entirely new chemistry, although implementation of its principles often leads to innovation. It does, however, involve merging tools, techniques, and technologies that can help chemists in research and production to develop more eco-friendly and efficient processes. The green chemistry necessitates a paradigm shift from our traditional concepts of process efficiency, say that focus primarily on chemical yields, to a paradigm that assigns economic value to eliminating waste and inefficiencies at the source and avoiding, where practical, the use of hazardous or toxic substances. And I'm sure many of you have seen the 12 principles of green chemistry. These were developed by Paul Anastas and John Warner in their classic text, Green Chemistry Theory and Practice. And I'd like to very briefly go over these 12 principles. Number one, which I strongly believe in, is that it is better to prevent waste than to treat or clean up the waste after it's formed. So simply put, this is stating design the waste out of your process. Principle number two states that your synthetic method should be designed to incorporate all of the materials used in the process into your final product. So in essence, it's about atom economy. Everything that you put into the reaction pot should end up as part of that final product. Principle number three states that your process should avoid the use and generation of toxic or environmentally damaging substances. Principle number four states that your product should be as effective as possible with as little toxicity as possible. Principle number five states that auxiliary substances should be avoided wherever possible. And auxiliary substances can include things such as solvents. Oftentimes, solvents are used as simply dissolution agents or as heat transfer agents. Principle number six states that we should take the energy requirements of the system into account. Oftentimes, reactions are done at sub-ambient temperatures simply because that's the way we learn to do the reactions in graduate school. Sometimes they're done at high temperature for the same reason. But simply try to see if your reaction can be carried out at ambient temperatures. Principle number seven states that raw materials should come from renewable sources wherever possible. Currently, over 95% of all the chemicals that are used come from petroleum products. As you well know, we don't have an infinite supply of petroleum, so let's try to use renewable chemicals derived from renewable resources wherever possible. Principle number 8 states that we should avoid derivatization wherever possible. Derivatization adds steps, it adds man-hours to your process, and it adds waste. So you put a protecting group on or a derivative on, that's one step. You have to take it off at another step. Principle number 9 states that we should use catalytic reagents wherever possible, and I think this only makes sense, catalysis as opposed to stoichiometric reagents. And principle number 10, and I think this is a very important point, that we should try to design our products such that at the end of their lifetime, they can be reused or that they can break down into harmless products, which hopefully we can use as a starting material for something else. Principle number 11 states that we should use real-time in-process monitoring wherever possible, and this helps to prevent the formation of waste materials. And finally, we should use materials that avoid harmful releases, fires, explosions, whatnot, and I think that certainly makes great sense there. So during the last few years, during the last few months rather, EPA has really redefined how we're going to do research. There are 6 programmatic areas that have been developed very recently, and one of these programmatic areas is chemical safety for sustainability. And this is all about what we're trying to do in this program is to improve the design and the manufacture of products in a safe and a sustainable way. So this is a really important area where business and government are coming together. And EPA's computational toxicology and the Office of Research and Development teams have been leading on this for quite some time and working quite closely with the Office of Chemical Safety and Pollution Prevention. So one of the key goals here is to advance green chemistry practice and to help shape future generation of safe products. So our long-term goals here are quite clear. And number 1, that is to move green chemistry and green engineering approaches into widespread use. Number 2, to avoid adverse impacts to human health and the environment through the improved design of processes and products. Number 3, to promote innovation and economic development. And finally, to improve the competitiveness of U.S. products on the global market. So, as I said before, green chemistry and green engineering requires a paradigm shift in our thinking to occur. So back in the early days, back in the 50s, if we wanted decaffeinated coffee, well, we got that decaffeinated coffee due to a process which involved extracting extracting the coffee beans with methylene chloride. So you see a factory here on the left side of your slide, where such extractions are carried out. Now, applying the principles of green chemistry, we then move to the center picture, where the coffee is decaffeinated via extraction with supercritical carbon dioxide. Okay? Now that represents a huge shift in terms of green chemistry. We're going from a somewhat toxic compound to a relatively benign solvent to do the extractions. But the true paradigm shift occurs when we can engineer the coffee bush to produce coffee beans which contain no caffeine. That's the type of paradigm shift which should occur in order to ensure that we're embracing all the principles of green chemistry. Now, what's going to be, or what is the EPA approach in terms of leading in green chemistry? Well, we're going to lead by example. We're building up an internal research effort. We're ramping up our green chemistry capabilities. In terms of our chemical safety for sustainability program that I briefly described, we're going to look at the inherent properties of chemicals, the inherent properties of products. We're going to take into account the life cycle considerations of chemicals, the life cycle considerations of products. We're going to increase the number of research collaborations that we enter into. So we're looking at industry, interagency collaborations, as well as academic collaborations. And finally, and most importantly, I think, is that the technological innovations that come out of EPA will be commercialized. Once industry picks up on these innovations, once one industry picks up on the innovation, another industry will follow suit. So we think that this is the way to make us a leader in the green chemistry arena. So how can we help lead? One of the first things that we have to do is to create a toolbox that others can use. So I'd like to tell you a bit about some of the tools. This is a mere sampling of some of the tools that EPA has in its arsenal. And I would encourage all of you who are viewing this to copy down the website at the very bottom page right now as I describe this tool, because it's definitely something that you'll want to use. So we developed a software tool called TEST. TEST is an acronym for Toxicity Estimation Software Tool. So there is a need to provide an estimate for toxicity values for a wide range of compounds. I can tell you that having worked in the pharmaceutical industry for some 22 years, I made thousands of new compounds, and I had only a very limited knowledge of or estimation as to what the toxicity of some of these compounds might be. TEST is a software tool that you can plug the structure of your molecule into, and TEST will give you some estimation as to the toxicity effects associated with that molecule. So it allows for a very quick estimate of acute aquatic toxicity, acute mammalian toxicity, and it also gives you an idea of the mutagenicity of that compound. And I can tell you that just within the last year or so, we've had over 1,400 downloads of this software, and it's currently being used by researchers all over the world. So again, a very important piece of software, and I encourage all of you to download this software and to use it. Well, if you're a user of chemicals, I would encourage you to download it and to use this on a daily basis. The next tool in the EPA Green Chemistry Toolbox is it's called our Waste Reduction Algorithm, and we abbreviate that as WAR. And again, if you look at the bottom of the slide, I'd encourage you to copy down this website, to go there and to download this software. And WAR is a piece of software which will allow you to calculate the potential environmental impact of your process. That process may be a chemical synthesis. It may be, I don't know, just making any new compound, candy, whatever. But basically, WAR looks at the inputs and the outputs of your process, and it gives you an estimation as to the potential environmental impact. Now, the impact areas that WAR looks at include human toxicity. What happens, if you ingest it, inhale it. Ecological toxicity, that is aquatic, terrestrial. Global atmospheric impacts, that could include global warming, ozone depletion, as well as regional atmospheric impacts, which could include acidification potential and photochemical oxidation potential. A third tool that EPA has in its arsenal is called PARIS-2, which is the program to assist the replacement of industrial solvents. Unfortunately, PARIS-2 is not available to the public right now, but we're working on a version which will be available to the public very soon. So I'd encourage you to kind of keep your eyes and ears open for that. But PARIS was designed to be a program which could give you a suitable alternative to the solvent that's used in your process. So what this program allows you to do is to tell it what is so important, what is the important parameter, what is the important feature of that particular solvent that you're using, and then PARIS-2 will suggest either a single solvent replacement that has a decreased human health and environmental impact, or it will suggest a mixture of solvents which has a decreased human health and environmental impact. So again, a very important piece of technology that's available to EPA scientists and that we plan to make available to the public in the very near future. So I've told you about a mere sampling of some of the tools in our toolbox. I'd now like to share with you some of the practical applications of some of the work that we've done at EPA. And one of the first examples I'd like to share with you is our catalytic ozone technology. So we were approached by a pulp and paper mill industry very recently. This industry was emitting some 100 million pounds of pollutants into the atmosphere every year. The pollutants that were being emitted were NOx and SOx, and as you all know, NOx and SOx enter the atmosphere. They get converted into nitric acid and sulfuric acid, respectively, and contributes to acid rain. Additionally, methanol was being emitted into the atmosphere. So we developed a novel catalytic ozone technology, which then allowed us to capture all of the SOx. It eliminated the generation of all NOx. And additionally, the methanol, which was being emitted, was converted to methylformate. The company could capture this methylformate and then sell this methylformate. So we took a waste stream and converted that waste stream into a value-added stream. And one of the things that I'd like to point out is that all the technology that we develop is considered a tool that can be used across many industries. So this technology is good for the pulp and paper industry, but there are also other industries that this same technology can be applied in. The next tool that I'd like to share, or the next technology that we developed, is our membrane-assisted vapor stripping for biofuel production. So in the current ethanol production facilities, the recovery of ethanol from dilute fermentation broth and drying of the ethanol to meet fuel standards requires a significant amount of energy. And this energy demand increases when certain types of biomass, for instance, lignocellulosic biomass, is used as a feedstock as opposed to corn. So scientists at EPA developed a hybrid technology, which we term membrane-assisted vapor stripping, which combines the best aspects of conventional distillation technology with the ability of new vapor permeation membranes to selectively remove water from alcohol mixtures. Now, the energy savings is greater than 50% using this technology. Again, this is a technology that can be applied in biofuel production. It's a technology that can be applied in the agricultural industry as well. So again, it's a practical solution to a real-world problem. Another area of research focus for EPA is in nanotechnology. Now, nanomaterials are ubiquitous. They're everywhere today. And so there is a need to evaluate their potential environmental impacts across the entire life cycle of this material. So to that end, we have embarked on a life cycle assessment of nanomaterials. That's an ongoing process, and we should have some data out on that in the very near future. Since we're talking about nanomaterials, I'd like to show you this slide, whereby we've developed a novel catalytic system for water treatment. So we have a titanium oxide nanocatalyst. This material is activated by UV light in water, and so what it can do is to then oxidize man-made pollutants such as dyes or pesticides or pharmaceuticals or solvents or whatever, but it will oxidize these materials back to carbon dioxide and water. So this is a greener, sustainable, and more economical approach for water treatment. And this technology has a very high potential to be used in developing countries. Again, with our nanomaterials, we decided that we need to synthesize these nanomaterials in a sustainable method. Now, traditionally, nanomaterials have been made by taking a metal halide, slurried in an organic solvent. You then add a reducing agent, typically sodium borohydride, and then you typically add some type of organic capping material. So organic solvents, reducing agents, organic capping agents, and sometimes these materials are quite toxic. So what we've developed at EPA is we've seen that we can slurry these metal halides in water, and then we can use a compound that's commonly found in nature as our reductant and as our capping agent. Vitamin B1 is one such agent. Vitamin B2, glutathione, all of these can be used in the synthesis of nanomaterials. So now we've eliminated the use of a toxic reducing agent, and we've eliminated the use of a potentially toxic capping agent. We've eliminated the use of organic solvents. And so what you'll see here is that based on the metal used, we can make nanomaterials of different sizes and different shapes, and hence they can be used in a variety of applications. Well, that was a nice green synthesis of nanomaterials, but you know, we always challenge our scientists to innovate on their innovations. And this is a very unique solution, I think, to the synthesis of nanomaterials, a story that I generally like to tell. The wine industry and the juice industry ends up with a lot of waste grape skin. And we were interested in seeing if we could do something with the waste red grape skins. So recognizing that these red grape skin contain lots of polyphenols, we decided that we could use these polyphenols as both a capping agent, as a reducing agent, and a capping agent. So now what we're able to do is take an aqueous slurry of metal halide, take a slurry which was made from the waste grape skins, simply mix those two, and voila, we generate nanomaterials on the spot. So to date, this is the greenest synthesis of nanomaterials known, and that was developed right here at EPA. Here we see that the nanomaterials can be used in green remediations. Okay? A small company, Veritech, up in Connecticut, picked up on our green syntheses of nanomaterials, and they're now making their nanomaterials using the methodology that was developed right here in EPA, and they're using these nanomaterials to clean up contaminated soils. And this is certainly an example of EPA technology which was used to help create jobs in the U.S. So we're quite proud of this technology. Now, continuing on with the nanomaterials, we were not the first to make these nanomaterials which were magnetic. They have an iron core, but we were the first to show the synthetic utility of these materials. So what you see here is an aqueous solution with our nanomaterials. We have two reactants in. They're vortexing. Here, after reaction is done, we simply stop the vortexing. The nanomaterials sink to the bottom of the test tube. We also cut the heat. And here, we apply an external magnetic field. In this case, we simply stick a magnetic stir bar on the outside of the test tube and slide all of the nanomaterials up and out of the reacting test tube. And here we see that on cooling, the product crystallizes out of the water, and so all we have to do is to filter. And I can tell you that we reuse this nanomaterial catalyst for up to 12 recycles, and we've seen no loss of activity. So this material is quite good for chemical synthesis. Another example of green chemistry at EPA is our development of what we call Sorpster. We obtained a waste adduct from the petroleum industry, and we were able to show and to demonstrate that this waste adduct could remove metals and a number of other compounds from water. So we can apply this to, at least on a theoretical basis, this waste material can be used to purify water. 12 jobs were created as a result of this technology. So, from this presentation, I think that we can see that green chemistry is all about innovation. It's about understanding the impacts of what you do. It's about decreasing the amount of waste. It's about actually preventing the formation of waste. It's about using the proper materials, making sure that your materials are safe, don't present any hazards. It's about eliminating the hazards. Green chemistry is all about eliminating the risk. It's about looking at the energy considerations associated with the process. And green chemistry is about understanding the environmental impacts of what you do. And once you embrace the principles of green chemistry, the cost of your process will go down substantially. So again, I'd like to thank you for your very kind invitation and for your very kind attention. I'd like to point out that one thing that we do here at EPA, one thing that we do quite well, is to innovate on innovation. So I want to thank you for your attention, and I would like to encourage you to look for our publications in the chemical literature. I'll be happy to answer any questions now.
Thanks, John. That was really, really very interesting. And I have some questions, but I'm going to take the prerogative of being the moderator here and ask you one question myself before we kick off, and that is, I saw that you, in your example about the coffee and the decaffeinization,
yes,
when we end up with a bush of beans that are not caffeinated, so I'm wondering whether that's a product of genetic engineering, or is it sort of the more, I mean, are genes added or spliced or things like that, or is it more along the lines of what we're familiar with in just creating hybrids from, you know, different variations within the same species?
Yeah, so that came from creating hybrids. But the point that I was trying to make here is that, it's the green chemist who said, well, using supercritical fluids, supercritical carbon dioxide to extract the caffeine out is good, but there must be a better way. It's actually the chemist who thought, why can't we have a bush which makes coffee beans without caffeine? And it's the same kind of thing, Lynn, in that instead of, most people have to cut their grass a couple times a week in the summer. Well, okay, you're using a power mower, which emits all kinds of noxious fumes and gases, contributes to global warming and such. So then you move to an electric lawnmower. Okay, well, that's great. That's a really good advancement. But the true solution then is to have grass which only grows to 2 or 3 inches and which stays green all year. So what I was trying to get at, it's that next level of thinking that has to be applied to every system.
Great, thank you. One of the questions that I can answer is that will these slides be available? And we have taped both the presentation and we'll be posting the slides on our website. I can't promise you when that will be, but they will be accessible on our website, hopefully in the near future. So one of the first questions that was asked is, how do you quantify the structure of a component, which I think is in reference to your first tool in terms of assessing the toxicity of a particular chemical?
Oh, okay. That's through a QSAR. That's through a QSAR model, and it's all hierarchical clustering. So basically, the test searches a number of databases. It sees how close your structure is to a compound which has known toxicities, and it makes a prediction based on how close your molecule is to the known molecules.
I hope that answers your question, and if not, you can post a follow-up. The same questioner also asked, will WAR, W-A-R, expand the ecological toxicity in chronic endpoints?
I'm sorry, Lynn, there was something that happened. I didn't hear all of the question.
Will WAR, capital W-A-R, expand ecological toxicity to chronic endpoints, as opposed to just the acute, I think, endpoints that you mentioned?
Well, we're looking for ways to expand on WAR, and that certainly could be one area that we may want to expand into. I'm not going to say that we're not going to do that, but we're looking to improve all of our tools at this point, and that could.
Yeah, I mean, I think there's a lot of concern about the chronic endpoints, which are much less easy, much harder to quantify and to deal with if there are, lag times, and sometimes it's the chronic that is more, more obscure than the
Yes.
acute.
Right.
So another question that we had is, where can the publications and literature be obtained? I think that you referenced in your presentation.
Sure. Well, I would certainly encourage people to go to the EPA website, epa.gov. I know that there is a repository for our publications. One thing that I can tell you all, a lot of the technology that I described today, though not all, was developed within the Sustainable Technology Division. So if you go to epa.gov and kind of navigate your way down to the Sustainable Technology Division, then you'll be able to find a list of all of our publications. But I would encourage you also to just go to our EPA website and in the search engine, just enter green chemistry publications. But certainly you can navigate there by going to the Sustainable Technology Division.
Great, thank you. So another question, which is very interesting, are you doing any work on applying green chemistry principles to shale gas fracking, to the shale gas fracking process? For example, designing less hazardous fracking chemicals or alternative methods?
I can tell you, Lynn, that, and whoever asked the question, that the fracking is being carried out in another division, and we've certainly had some conversations regarding green chemistry opportunities there. So at current, I do not believe that there's any green chemistry efforts, but that is something that we have been talking about, and I would not be surprised to see some activity there in the future.
I think that a lot of us will be looking forward to that, because I think, it's pretty clear that the fracking is a pretty huge issue right now.
Absolutely.
And it would be good to see some progress on, on reducing the impacts of that.
Yes. So one thing that EPA is committed to doing, and that is to solving problems of national significance, and certainly fracking is an issue of national significance, and we would like to certainly solve this issue in a very sustainable manner.
Great. So a little change of direction here. We have a comment just saying that this is an excellent example to be used in a green chemistry class for chemistry majors, and thank you for that. But the question is, are any educational internship programs that are there any educational internship programs that EPA offers to undergraduates to secure hands-on experience, lab experience in some of the things that you've been talking about today?
Oh, absolutely. Part of being a leader, Lynn, is to teach others, And one of the things that we do like to do is to get people as early as possible and to bring them within the green chemistry fold, so to speak. So yes, we do have opportunities. They're internships, and if people would like to come, we certainly welcome undergraduates, and we have a number of undergraduates working in our laboratories right now. Additionally, we have collaborations with academic institutions. So there are a number of opportunities for undergraduates to work in the green chemistry arena within EPA.
Well, that's really good to hear, because as I hope most of you know, we're getting going with our Great Lakes Green Chemistry Student Network, which has a home now on the Michigan Green Chemistry Clearinghouse website, and that's just the kind of information that we'd like to make available, John. So maybe you could send me some specific details, and we can then post them on the Great Lakes Green Chemistry Student Network tab on the Michigan Green Chemistry Clearinghouse website that Clinton gave you the URL, which is migreenchemistry.org. And if you look under education, you'll see a tab for the Great Lakes Green Chemistry Student Network, and we really want to post opportunities like that and make things, let everybody know and let students know what's available for them out there, and how they can, where they can contact you if there are application forms and information, how they would go about setting that up.
Sure, Lynn, I'd be very happy to send you that information. Unfortunately, it's just not right at my fingertips right now. But we can send you that information. I can tell you that we're always willing to work, with students, with faculty. That's part of being a leader is educating other people, and we certainly believe in that.
I did get a comment about the chronic endpoints, and I am reading it because I do think it's really important in the discussion of testing chronic versus acute, and not necessarily versus, but certainly in addition to, because as the commenter says, chronic endpoints are much more relevant to evaluation of potential impacts, and I think that we're finding that to be true, especially since we probably have a far better understanding of the acute impacts of a lot of chemicals,
yes, rather
than the results of long-term chronic exposures.
Yes, and so Lynn, I will respond to that. What we have developed is our first generation tool, and we can take these tools to the next step. But this is what we have in the toolbox right now, and we will develop these tools a bit more. But I understand the concerns, and these are conversations that our scientists have had, and these are some issues that that we can begin to address. Other agencies within the EPA are also looking at these issues as well.
Great. So we still have some time left if there are any other questions to ask John.
Lynn, there is a question I think that you skipped over.
Oh, I did. I'm sorry. Which?
There's one about how does green chemistry address trade-offs?
Oh, I don't see that one. Okay, thank you.
How does green chemistry address what?
Well, I'll read it out for you, just in case
Please do.
you can't see it. The question is, how does green chemistry address trade-offs? In other words, if a green process produces substantially more greenhouse gases and consumes more energy than a process that involves a known toxic chemical that has superior performance in these areas, what takes precedence?
I can't tell you what takes precedence, but I can tell you that the process, you have to look at the full the life cycle of that product. You have to look at all the implications of of those byproducts that are being generated, and it's more or less kind of tallying, to find out what are the environmental implications of this process, what are the environmental implications of the second process, and so that's one of the things we do is we sit down, we look at these, we look at the metrics, we look at the indicators, and we simply compare which is the more sustainable process, which is the greener process. So, at this point, I can't tell you which one, what takes precedence. There are a number of factors. Right now, we're developing a software tool which may help us do that. And that software tool is called Green Scope. You should see something in the literature in the next few months regarding this, but I just, at this moment, cannot tell you what takes the priority. Any other questions?
I'm not seeing any other questions. This is your last chance. It's been a great presentation, John, and sometimes I think there aren't questions because you really covered all the bases. Wait, I have another question. Question for John. What synergies exist or could exist between what is being done in the Sustainable Technology Division and other EPA efforts?
Sure. Well, there are a number of synergies. I only focus today on green chemistry. And green chemistry is simply a portion of what we do here. So we have a huge effort now in what's called green infrastructure. Basically, how we manage water, how we manage stormwater runoff, how we manage combined sewer overflows. Okay, this division is heavily involved in that. So, we've partnered with the water division in this effort. We've partnered. We're also doing investigating water quality trading. So that represents an opportunity right there. And as I said, we developed a catalyst to help disinfect or help purify water. Again, another great example of how we can work, say, with a water division. The nanomaterials, we can partner with the land division in terms of remediating contaminated soils, okay, and that's a cross-divisional effort. We are partnering with the computational toxicology group, which is developing some very refined software for calculating toxicology. So there's a plethora of opportunities for the Sustainable Technology Division to partner with other divisions within the EPA and other.
One thing that comes to mind right away for me is what your relationship is with Design for the Environment, because that would seem to be one of the more obvious divisions where there might be some synergy. Can you comment on whether whether any project
in that arena? So the DFE, that's really up and coming. But yes, we have a number of chemists involved in that area. So basically, what I'm saying is the Sustainable Technology Division is all about sustainability, and right now, sustainability is one of it's a key program within EPA. So we've got our fingers in many different pies. We're always looking to other offices, to the regions, to other divisions, other labs, to work on these integrated transdisciplinary research projects. So.
And how does your division decide what to do? What's the process for deciding to work on one thing? Do other divisions bring you questions and problems, or how do you decide where your research is going to be going?
Yes. Well, first of all, then the research paradigm is changing within EPA. It is driven by the needs of the program offices and the regions. But again, I'd say more importantly is problems of national concern and national significance. That is the that's the major driver here. Again, we look for opportunities to partner with others. If we have specific expertise that another group needs, we will certainly lend that expertise to that group. If we just happen to see that that there's an easy fix from another group that we can make, we will just go in and tell these people, we can help, or oftentimes they will come to us for help. Our scientists, there are a number of quote internal grants, and scientists or the PIs from the various divisions we'll meet at lunch or other conferences, talk, discuss their research, and see where they can help each other, and they will co-author grants, to see if they can jointly solve a problem. So there are many.
That's great. We're getting close to the end, but what that makes me think is going back to the fracking issue, whether NGOs and other scientists can make proposals to your office of specific things that we might like to see be addressed in the research in the future. So that's just a thought.
Yeah, I see what you're getting at, Lynn. And again, if the program offices tell us that this is something that they would like to see solved, if the regions tell us that there's a particular problem that they'd like for us to solve, then we'll make sure that we put some manpower on that if it's available.
Great,
Absolutely.
Thank you. That's very helpful.